Welcome to Podcast Learn and Fun. Let's start today's journey of learning. I was reading about this concept called zero-point energy, and honestly, my mind is blown. Have you ever heard of this?
Oh, absolutely. Zero-point energy, or ZPE, is one of those things that really highlights how strange and counterintuitive quantum mechanics can be.
Yeah, I'm getting that vibe. It's like I thought absolute zero meant things were frozen, like completely still. But ZPE says there's still some energy hanging around. How is that even possible?
Right, that's the thing. It really messes with our everyday understanding of cold and still. We aren't talking about heat in the way we usually think of it. We're talking about a fundamental energy that quantum systems possess, even at their absolute lowest energy state.
Okay, so even at the most chilled out state imaginable, there's this base level of energy that just can't be taken away. That's wild. So where does it even come from?
Well, imagine a tiny spring. And even when it's as cold as physically possible, it's still kind of vibrating. That's a simplified way to think about ZPE. And the reason behind this constant jiggle is the Heisenberg uncertainty principle.
Oh, right. The one that says you can't know both a particle's position and momentum with perfect accuracy at the same time.
Exactly. And because of this fundamental uncertainty, a particle can never truly be at rest. There's always some inherent, unavoidable motion, even at absolute zero. And motion means energy. That's ZPE in a nutshell.
So this isn't some energy we haven't figured out how to get rid of. It's like the universe has a minimum energy setting.
That's a great way to put it. And this has some really interesting implications. One way to understand this better is through the quantum harmonic oscillator model.
Okay, I'm ready. Lay it on me.
Well, think of it like this. The quantum harmonic oscillator is a model we use to describe how particles behave in certain systems. And what's fascinating is that the energy levels of this oscillator are quantized.
Hold on, quantized. Does that mean they come in specific discrete packets of energy and not just any random amount?
You got it. It's not a continuous spectrum of energy, but rather specific allowed energy levels. Think of it like steps on a ladder. And this is where the Schrödinger equation comes in.
Ah, the famous equation that governs the quantum world. I knew we'd run into that eventually.
Right. It's this equation that lets us predict these quantized energy levels, including the lowest one, which, as you might have guessed, is the zero-point energy level.
Wait, so the ground state of this oscillator, the very bottom rung of the ladder, isn't zero energy. That seems counterintuitive.
Right. It's the lowest possible energy the system can have, but it's not zero. And the wild thing is the value of this zero-point energy isn't just some universal constant. It's actually determined by the characteristics of the system itself.
So depending on the type of particle or the strength of the forces acting on it, the ZPE will vary. That's incredible. But what does this all actually mean in the grand scheme of things? How does this tiny jiggle affect anything in the real world?
That's where things get even more interesting. It really does touch on something you said earlier. The idea that this seemingly insignificant jiggle at the quantum level could actually have tangible effects in the real world.
Yeah, it's just mind-boggling to me. How can this energy that's so fundamental, so deeply embedded in the fabric of the universe actually manifest in ways we can observe or even potentially utilize?
Well, for starters, it plays a role in the stability of matter itself. The fact that atoms don't just collapse in on themselves is partially due to this residual energy preventing electrons from spiraling into the nucleus.
Wait, hold on. So you're telling me that this tiny bit of ZPE is essentially what keeps atoms from imploding? That's insane.
It's pretty remarkable, right? But it doesn't stop there. ZPE also plays a crucial role in chemical reactions. It contributes to what's called the activation energy. That's the energy barrier that needs to be overcome for a reaction to occur.
So this quantum jiggle is influencing how molecules interact with each other, and even how fast or slow chemical reactions happen. I'm starting to see how this seemingly abstract concept is actually woven into the very processes that make life possible.
Exactly. And it gets even weirder. Remember we talked about how the value of ZPE depends on the characteristics of the system? Well, when you bring two uncharged metallic plates very close together in a vacuum, something fascinating happens.
No, I'm intrigued. Tell me more.
The ZPE of the electromagnetic field between those plates is actually modified compared to the ZPE outside the plates. This creates a pressure difference, a force that pushes the plates together. This is called the Casimir effect, and it's one of the most direct experimental confirmations we have of the reality of ZPE.
Wow, so we're not just theorizing about this energy, we can actually measure its effects. That's incredible. But I have to ask, if there's all this energy in a vacuum, wouldn't that mean there's an infinite amount of it? That seems like it would break some fundamental laws of physics.
That's a great question, and it gets to the heart of some of the biggest mysteries and debates surrounding ZPE. The theoretical calculations for the energy density of the vacuum based on quantum field theory actually predict a ridiculously huge value.
Like astronomically huge.
Way beyond that, so huge that it would create a gravitational field strong enough to curl up the entire universe. Obviously, we don't see that happening.
Yeah, that's a slight problem. So what's going on? Do we just not fully understand ZPE? Or is there something else at play here?
That's what physicists are trying to figure out. There are a lot of ideas out there, some more mainstream than others. It could be that our current understanding of quantum field theory is incomplete, or that there are some unknown mechanisms that suppress this enormous vacuum energy. There's even speculation about the possibility of extra dimensions and their role in this.
Whoa, extra dimensions. Now we're talking. So this seemingly simple concept of ZPE is leading us to some of the most profound mysteries in physics.
Absolutely, and it doesn't stop there. ZPE is also thought to have implications for cosmology and the expansion of the universe. Some physicists believe that the mysterious dark energy that's driving the accelerated expansion of the cosmos could be related to the energy density of the vacuum.
So this tiny jiggle at the quantum level could be connected to the fate of the entire universe. That's a pretty big leap.
I know, it's mind-blowing, right? But that's the beauty of science, exploring these connections between the smallest and largest scales of existence.
This really makes you wonder what other secrets are like, hidden within this seemingly simple concept of zero-point energy. I mean, we've talked about its role in the stability of matter, chemical reactions, the Casimir effect, even the expansion of the universe. What else is there?
Well, one of the biggest questions that has captured the imaginations of scientists and the public alike is whether we could ever harness zero-point energy for practical use. Imagine tapping into this vast reservoir of energy that exists everywhere all the time. It would be revolutionary.
It would be like something straight out of science fiction. Free, limitless energy. Sign me up. But is that even remotely possible, or are we just talking fantasy land here?
It's certainly a tantalizing prospect, and there has been a lot of speculation and research into this, but there are some major challenges, both theoretical and practical. For one thing, some physicists argue that extracting usable energy from the vacuum might violate fundamental laws of thermodynamics.
So even if we figure out the engineering up, there might be fundamental physical laws that prevent us from actually tapping into this energy source.
That's a possibility we have to consider. But even if harnessing zero-point energy for, say, powering our cities or spaceships turns out to be impossible, the study of ZPE is incredibly valuable in its own right.
Yeah, I can see that. It's already given us insights into some of the most profound mysteries in physics, and who knows what other discoveries await us as we delve deeper into this realm.
Exactly. Zero-point energy is intimately connected to other areas of active research, like quantum field theory, cosmology, even the search for a unified theory of everything. It's a concept that bridges different scales of reality, from the subatomic to the cosmic.
It's almost like a key that unlocks a deeper understanding of how the universe works at its most fundamental level.
That's a beautiful way to put it. And as our experimental techniques and theoretical models continue to advance, I have no doubt that zero-point energy will continue to surprise and challenge us, revealing even more wonders about the nature of reality.
Well, I'm definitely hooked. Zero-point energy has gone from being this mind-boggling concept to something that I feel like I'm starting to grasp, at least in a small way. It's definitely made me look at the world a little differently. Knowing that this hidden energy is all around us, constantly buzzing away, even in the seemingly empty vacuum.
That's the power of scientific inquiry, isn't it? It allows us to see the familiar in new light, to appreciate the hidden depths of reality. And who knows, maybe someday we'll unlock the secrets of zero-point energy in ways we can't even imagine right now.
I can't wait to see what the future holds. Thanks for taking us on this incredible journey into the world of zero-point energy. It's been a truly eye-opening experience. Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.